Hello, this is me, Dr. Abhigyan Ganguly, and I am working as a postdoctoral fellow at the University of KwaZulu-Natal, Durban, in the Department of Electronics and Communication Engineering. My research topic is nanoelectronics, more specifically quantum dot-based solar cells and light-emitting devices. This presentation is on the paper titled Improved Efficiency Solar Cells Using Iron Doped Zinc Sulfide Quantum Dots as Sensitizer. Uh, the authors are myself, Abhigyan Ganguly, and Dr. Viranjay M. Srivastava. So without further delay, as the time is limited, let's go into the presentation. With increasing population and advance in technology worldwide, the power consumption of worldwide is increasing. Now, the main source of power, that is coal and petroleum, are non-sustainable. On the other hand, uh, one, sun provides about 10,000 times more energy than our global annual consumption, energy consumption. Hence, scientists are looking forward to using or harnessing the solar energy. But the problem with normal silicon solar cells is that its fabrication cost is very high because it requires a single crystal of high purity. So as a result, photovoltaic researchers are looking forward to emerging technologies. Emerging technologies in solar cells can be fabricated on thin flexible bases using more straightforward and simple low-cost solution-based techniques. Also suitable for using a wider range that we'll see. So among these emerging technologies, the derivative of third generation solar cell is quantum dot sensitized solar cell, which is considered to be one of the most promising. We'll see why quantum dot solar cell is considered to be most promising. So why quantum dots and why they are used in solar cell? So quantum dots are basically zero-dimensional semiconductors that are spatially confined in all three dimensions. That is, if we go on reducing the size of any material in all the three dimensions to form just a dot, almost as virtually zero-dimensional material, then it can be termed as a quantum dot. So using semiconductor quantum dots as a sensitizer in solar cell, we have the following advantages. Firstly, a wider range of solar spectrum can be utilized because in normal solar cell only the light is absorbed from the visual range, while quantum dots absorbs lights. The absorption starts from that of the UV visible region, UV region. So the a wider range from ranging from UV to that of the visual light can be utilized in case of quantum dot solar cells. Also, the band gap can be tuned to match the oxide. One of the most important property of quantum dot is that if we go on reducing the size of quantum dot, the band gap increases. So we can actually tune the band gap of sensitizing material, that is quantum dot, to match that of the depositing oxide. As we can see in this figure, by reducing the size of lead sulfide quantum dot, the band gap increases. And we know the electron jump is easier from higher energy to that of the lower energy compared to lower energy to that of higher. So, and another advantage is that quantum dots are highly stable towards water and oxygen, which is the main disadvantage of third generation dye-sensitized solar cell. Theory and physics. Our main objective of as a photovoltaic researcher is to increase the efficiency of solar cell. One of the common method that is used recently is by doping the quantum dot using transition metal ion. Why transition metal ion? Because the transition metal ion has a property called photo-assisted DD transition. That is, when a light falls on a transition ion, the NS electron is removed first before leaving behind the unpaired N-1 D electron. This unpaired D electron can move from the d orbital of 1 to the d orbital of the adjacent orbital. And this extra d orbital electron actually contributes to increasing the current in case of doped quantum dot solar cells. Now, for our present work, we will consider zinc sulfide quantum dots. We'll dope them with iron, that is iron, that is one of the transition metal, and fabricate solar cell using both the doped as well as the iron doped zinc sulfide quantum dots and test them under similar conditions and see if there is an increase in efficiency, and if there is an increase in efficiency, then how much is the increase in efficiency? Is it even significant? So synthesis, first the synthesis, chemical synthesis process of zinc sulfide quantum dots. We use a simple one-pot synthesis chemical method. The matrix, that is the capping matrix used here, is the PVP, that is polyvinyl pyrrolidine. The main function of this PVP is to control the size of quantum dot, because the reaction, the growth of quantum dot takes place in the interstitial gaps of the PVP, while PVP does not take part in itself in the reaction. So we prepare a PVP solution, give it a 1 day standing time, and on that we add zinc chloride, and then we add sodium sulfide. This zinc chloride and sodium sulfide reacts together to form Zns quantum dots, while the other byproducts are soluble, water soluble, so they can be easily separated and washed away. And for doping purpose, we add 4% by weight, that is a very trace amount of iron chloride, FeCl3, for where the iron ion acts as a dopant. After preparing this, we characterize the quantum dots, both the doped and undoped quantum dot. In the first figure, that is figure 1, we can see the UV visible absorption spectroscopy. You can observe that the absorption edge can be determined by drawing a tangent approximately from a point where there is a sudden increase in the absorption in case of quantum dots. So in normal, that is undoped zinc sulfide, the absorption is at 228 nanometer, while for doped zinc sulfide quantum dot, it is a bit of blue shifted. This little blue shift is due to increased nucleation rate on addition of dopant ions. This has been observed previously also in other related works. So the range starts, absorption range starts from around 200 nanometer. That is, it is actually the UV region. And in the figure 2, we can see the XRD, that is X-ray diffraction spectra. You can see there is no observable change in the doped as well as in the undoped quantum dot. This is actually what we desired. We didn't want any to cause any kind of change or in the crystal on doping. So by obtaining a similar pattern of XRD, we can conclude that no changes has been occurred in the crystal due to doping. This is what we desire. And this is a HRTM, that is high resolution transmission electron microscopy imaging of the fabricated solar cells. You can see the size is around 10 nanometer, which confirms the formation of quantum dots. And the data obtained from the absorption as well as the XRD spectra is presented here. The approximate band gap is calculated from absorption using hyperbolic band model, and from the XID using Shearer formula. We can see that the average size of quantum dots approximated almost matches that of the actual size, that is in and around 10 to 11 nanometer. Now we come to the main part, that is fabrication of quantum dot solar cell. For fabrication, we first take a FTO glass plate to act as a transparent conducting oxide as a base. Then on that we add zinc oxide. The zinc oxide is deposited in situ by adding zinc acetate and sodium hydroxide in an ethanol solvent. Then it is annealed and heated so that the zinc oxide adheres better to that of the glass surface. Then we dip coat, that is, we just dip the oxide deposited glass plate, FTO glass plate, in the previously prepared quantum dot solution to form a quantum dot layer on that of the oxide. And finally, we add a polysulfide electrolyte, a few drops of polysulfide electrolyte, add two glass you know, spacers, so to prevent any kind of short between the photoanode and the next counter electrode. And finally, we sandwich it with the aluminum plate to form the solar cell. As you can see, we connect the cathode and anode terminals by using normal crocodile probes and test it within in illuminated white light condition by of a xenon lamp. Figure 4 shows the current density versus voltage characteristic obtained for the undoped as well as the iron doped zinc sulfide quantum dots based solar cell. So we can actually see from the curve that there is an increase on doping. The red curve indicates the doped, while the black curve indicates the undoped characteristic. Now, from this curve, we have determined the solar cell parameters, solar cell operating parameters, which are the fill factors and efficiency, the two important parameters, by using these formulas provided here. So in table 2, we can actually see that in case of normal zinc sulfide, undoped zinc sulfide, while the efficiency is around 1.52%, for iron dope transition metal iron dope zinc sulfide, the efficiency has increased to 2.73%. In terms of low cost photovoltaics, this is a significant increase. We can say this is a significant increase. So we can conclude that on doping of transition metal ions, that is Fe, on zinc sulfide quantum dot based solar cell, the efficiency increases. It gives a better result. Uh, Further research are possible based on our present work. For example, we can try different transition metal ions on zinc sulfide quantum dots. Here we have used iron. One can use copper or manganese on zinc sulfide quantum dots and see the result of increased efficiency. How much is the increase? Or one can use different quantum dots using the same dopant. That is, using they can dope iron ion into different quantum dot based solar cell. Or another avenue is one can actually mix and match. One can use co-doping, that is, may use manganese and copper or manganese and iron or copper, both in trace amounts, doping in quantum dots and test their result. So these are the future avenues, and with this we come to the end of our presentation. These are the references used for the work. Thank you.